Hi everyone, my name's Tempe and I'll be presenting my project on robot-assisted animal surgery that I did with Dr. Fulvio Forni. So today I'm going to take you through the 5 sections: the motivation, the statement of the problem, the 3 principal tasks that we use to solve this problem, the main result, discussion, and conclusion. So the objective is to explore the feasibility of using a robot to assist in accurate drilling during canine pelvis surgery. So why use a robot? Well, according to the World Health Organization, 25% of patients suffer complications after surgery, of which 63.5% are due to surgical techniques and inaccuracies. Now, of course, these inaccuracies arise because we as humans are limited. We have limited geometric accuracy, we are prone to tremor and fatigue, and although we have a lot of strengths as well, if we can complement our limitations with the robot's strengths, with their strong geometric accuracy, the fact that they're stable and untiring, we hope to minimize accuracy errors and reduce surgical complications. So what is it that we're trying to solve? Well, the first question we have to answer is, where do we drill? The robot needs to know the position and trajectory of a point to drill. And ideally, what we'd like to do is to be able to select a target in the virtual environment, like Slicer here, map this target on the 3D bone in the virtual environment to the real-world environment, to the bone in the real-world environment, and then tell the robot to take its drill, and then to go on its tool, take its drill, and then go to that position at a specific trajectory and then track that position. And I'll show you what I mean by tracking in the next slide, but for now I want to just talk about the software. So like I said, Slicer used to create targets in a virtual environment, RoboDK, which controls the robot, and we have Polaris Vicra, which is the camera, and that gives us the visual data that we need. So what is tracking? Well, this is very simple. So all we're saying is that we take the drill guide to a certain target that we've selected, and then if the bone moves, make sure that this drill stays at that target until I tell it to go to the next position. And that's what we do here. So you can see I'm moving the bone and the robot is realigning itself. That video is quite far away, so there is one a bit closer. You can see here that it's trying to track the point here. Right. Okay, so how do we go about doing this? Well, we split up the method into 3 principal tasks. We firstly establish an integrated software system. We create and linearly map targets in a virtual to a real-world environment. And then we plan the trajectory using visual data. So we've touched on the integrated software approach already, which is that we create targets in Slicer, we send them over to RoboDK, which controls the robot via a Python interface. We send it over using OpenIGT-Link, which is a data transfer protocol. And RoboDK is connected to the camera as well. Right, second task is to do the virtual to the real world mapping. And before we can do that, we have to split up the virtual and the real world into 3 spaces. So the virtual world is spanned by the image space, which is the coordinate system given by Slicer. The real world has the robot space, which is given by RoboDK, and has the patient space, which is given by Polaris Vicra. Of course, this is the same physical space, it's just relative to different frames. And ideally what we'd like to do is to select a target in the image space and map it to the robot space, right? So the robot knows where to go. And the way we do that is to map the image space to the patient space and then the patient space to the robot space. And to map any 2 spaces, we need 2 sets of corresponding points, points in each space. And then we use the linear least square solution to find the transformation that fits it best. Okay, so the first thing we do is image to patient mapping, and we need 2 sets of corresponding points. So we have these blue 12 landmarks here in the image space, and Professor Allen selected these out here, and he also selected out the 12 landmarks in the patient space, and they form the corresponding points. Now it's easy to get these blue landmarks in the patient space, in the image space, of course, because the Slicer gives us these coordinates. But how do we give the coordinates of the same point in the patient space? Well, we use this probe. And the way this probe works is that these 4 markers reflect infrared light, and once calibrated, I'm always able to obtain the XYZ position of this probe's tip. So you can imagine that if I just match the probe's tip to each of these landmarks for all 12 landmarks, I have my 2 sets of corresponding points, and I can just find the transformation between them. Okay, so now we want to map the patient to the robot space. And as we already have the probe that we use to find coordinates in the patient space, we have to get something that can give us the coordinates in the robot space. And we define a robot tool center point, which is just a physical point on the robot tool. And you can imagine that as it spans the same physical space, all I have to do is to match the probe's tip with the robot TCP at multiple points in the real physical space. And these form my two sets of corresponding points. And that's what I do here in this video. This is the probe, as you can see. I'm just matching the tip with the robot TCP. For multiple locations in space. Right. So now that we have a mapping from the image space to the robot space, we can now create targets that the robot will understand. Say the robot takes the drill to that target, at what trajectory should it be at? Well, I talked to Professor Allen, and he said that ideally the trajectory of the drill should come in at an angle that is normal to a plane that he can define. And he can define that using these points. He can create points in the image space in the virtual environment. We then use the transformation we've just talked about to map that from the image space to the robot space. We fit a plane of best fit, and then we tell the robot to go to the target at an angle that is normal to this plane. So now we have a way of creating a target, and we have a way of telling the robot at what trajectory it should be coming at. So what we do next is we actually do the drilling. Professor Allen selected 5 different targets, and we drilled them, and then we check for their accuracy later. Again, as that's quite far away, there's another video here of it, of us drilling much closer to the bone. Okay, so I slowed down the robot speed as well, so we can clearly see how it's moving from target to target. Okay. So now that we've drilled it, we want to compare the accuracy. So we take the drilled positions and we map it back into the virtual environment, and then we compare them to the initial target that we set. And what we find is that they're all consistently below 2 millimeters, except for this one here, number 5. And the reason for this was because we selected a target that was on the edge of the animal bone. So every time Professor Allen tried to drill that point, the drill kept slipping. But otherwise, they're all below 2 millimeters, and the average accuracy is 1.33 millimeters. The reason I keep saying 2 millimeters is because according to these 2 studies, the acceptable accuracy by a surgeon's opinion is about 2 millimeters. And the fact that ours is, has an average of 1.33 and all except 1 are below 2 millimeters means that this is a very acceptable result. And the efficiency of the algorithm, the time it takes for the drill guide to follow the points whilst tracking is about 0.2 seconds on average, so that is also very good. We were kind of we were considering why we couldn't get the accuracy to be lower, and the error to be lower. Sorry, and of course part of the reason of that is that when we're doing the mapping and the calibrations, they're not perfect correspondences. So of course these give rise to residue errors, and they will obviously affect our result as well. But another consideration is the fact that the robot itself, the KUKA, has an accuracy of about 1 millimeter, and this was estimated based on 2 different studies. And the fact that the accuracy of the robot itself is about that, and the positional accuracy that we got was 1.33, means that this is a very, very acceptable result, actually. So that's good. But there is, of course, room for future work. So we can make the accuracy better, we can calibrate better, we can do better mapping. We could use surface registration to do image to patient mapping. We could use laser tracking to calibrate the robot tool center point better. And there were some problems that we had with RoboDK when it came to kind of feedback control with the tracking. And it would have been better if we used ROS for that, because they offer a control module and you can set up a PID controller. And the other consideration that's also very important is working with soft tissues. So we assumed that it was a completely rigid body, which meant that our kind of calibration processes were relatively straightforward compared to what it would be if it were soft tissues. But that is something that could definitely be looked into. And I think this does provide a proof of principle and a good foundation for this, for another project to be built on. Thank you very much for listening.